Hello and welcome to 1.3, using reasoning to find a counterexample to a conjecture. So what we're really trying to do here is we're trying to invalidate a conjecture by finding a contradiction, by finding something, a counterexample that makes what the conjecture says wrong. So first we're going to start with this explorer. 6, 12, 10, 150. The conjecture is all but one of the vowels, A, E, I, O, U, and Y, are used to spell numbers. Gather evidence to support or deny this conjecture. So the idea is you can spell out any number. You can spell it 1, 2, 3. All of these numbers you can spell out, and you use every single vowel except one. There's one vowel that is not used. So is this true? Is this not true? Looking at the answer here, it says that the numbers the number words to 100 contain all the vowels except A. So if you look through, we have every single vowel. We don't use the letter A until the word thousand with the A there. That is the first number that contains the vowel A. So this conjecture seems to be true as you go along all the way up to 1000, but as soon as you hit 1000, we get an A, and in fact, all the vowels are used. So back in 1.1, we had Francesca and Stefan make conjectures about the difference between consecutive squares. Stefan had said that the difference between consecutive perfect squares was always odd, and Francesca said the difference between consecutive perfect squares is always a prime number. So what we're going to do now is we're going to test these conjectures. We're going to see if we can find a counterexample. Once we find a counterexample, we're going to know that their conjectures are false. So let's look first of all at Luke looking at Stefan's conjecture. So Stefan's conjecture was true for the pairs he tried. 2 and 2 and a 3 by 3, a 4 by 4 and a 3 by 3, and a 5 by 5 and a 6 by 6. So if you remember what we did before, drawing on a grid, he took a 2 by 2 square, he subtracted a 1 by 1 square, and he got the difference to be 3. So here we have Luke going through the steps. He says, first I tried a 1 by 1 and a 2 by 2. I made the same tile squares as Stefan. When I took away the yellow square, I was left with a pair of tiles that shared an edge with the yellow square and a single tile in the top right corner. So we had 2 pairs and 1. So, oh, that's one too many. He had, sorry, a pair of tiles and 1 more. Next, he did the 4 by 4 and the 5 by 5, the difference of perfect squares. Since Stefan had skipped over these values, I was left with 2 groups of tiles, each with the same value as the side of the yellow square. So each with the same value, 4 squares, which is the same as the yellow square, plus 1 extra tile in the top right corner. So we have 4 and 4 plus 1. I tried consecutive squares of 6 and 7. The difference again showed the same pattern. 2 groups of tiles, each with the same value as the side of the yellow square, plus 1 single square. These 3 examples support Stefan's conjecture. Remember, Stefan's conjecture was the difference between consecutive perfect squares is always an odd number. So Luke says that these support his conjecture. I visualized what the difference would look like for any pair of consecutive squares. There'd always be 2 groups of orange tiles, each with the same value as the side of the smaller yellow square, plus 1 unpaired orange square in the corner. The total value of the 2 equal groups would always be an even number. Since 2 times any number is even, the unpaired tile would make the difference odd. So I always have 2 times a number plus 1. And we're going to learn later that this is the generalization for odd. All of this evidence strengthens the validity of Stefan's conjecture. However, it doesn't prove the conjecture since he hasn't tried all possible cases. So Luke hasn't gone through and tried every single difference of consecutive squares. But he's done more work and he's even given us this nice visualization that helps strengthen that conjecture. So for now, we're saying, yeah, we believe Stefan's conjecture. But now we're going to have our good friend Pierre is going to look at Francesca's conjecture. Her conjecture was that the difference between consecutive perfect squares is always prime. So she goes a step further. She says not only are they odd, but they're also prime. They can't be written in as two factors. So for instance, the number 6 is not prime because it can be written as 3 times 2. But the number 3 is prime because it can only be written as 3 times 1. So Francesca used the consecutive squares of 1, 2, 3, 1 and 2, 3 and 4, and 8 and 9. So what Pierre did is said, wait a second. He did 1 and 2, he did 3 and 4, he did 8 and 9. He skipped over some things. Let's see if I try those numbers, what will come up. So first of all is he tried 3 and 2. Well, 3 squared minus 2 squared, 9 minus 4 is 5. So that one, yeah, that's prime. Looks like Francesca's doing her job. But the next gap was 4 and 5. So he did 5 squared, which is 25, minus 4 squared, 16, equals 9. Well, that's odd, but that sure is not prime, because 9 can be written as 3 times 3. Francesca's conjecture that the difference between consecutive squares is always a prime number was disproved since a counterexample was found. So the question I have right now is there other counterexamples to Francesca's conjecture? Can you come up with other difference of consecutive perfect squares that are not prime? And is there any way that you could find a counterexample to Stefan's conjecture and explain? So another example of a non-prime difference of consecutive perfect squares would be 8 squared minus 7 squared is 15. And there is no counterexample to Stefan's conjecture because Luke's visualization presents a strong argument for the conjecture being valid in all cases. Even though Luke's visualization does not prove the conjecture for all cases, it strengthens my belief that the pattern will be repeated. So we have yet to do a formal proof, but we are pretty convinced that this conjecture that the difference between consecutive perfect squares is odd is true. So the key idea is once you have found a counterexample, you have disproved a conjecture. This means that the conjecture is invalid. You may be able to use a counterexample to help you revise a conjecture. Here's something that's really important. A single counterexample is enough to disprove a conjecture. Think about when you have an argument with your friend. If they say all dogs are brown, you just need to bring one white dog and you have proved them wrong. Look, here's a white dog. You're wrong. Even if you cannot find a counterexample, so even if you try and look all over the place, all you can find is brown dogs, that you cannot be certain that there is not one. Any supporting evidence you develop while searching for a counterexample does increase the likelihood that the conjecture is true, but it does not prove it. We're going to learn to prove in a couple sections, okay? What I'd like you to try on page 22, I'd like you to try question 1, 3, 5, 6, 12, and 14. As well, I'd like you to read the history connection and answer A and B.